This is a tutorial video for the second question, moon pies. So in this question, you have n moon pies facing up in a row. Each pie is either facing up or facing down. In one move, Bessie can pick any consecutive subarray and flip all the pies in it. And we can add every time Bessie can make at most one move. The question is how many different number of facing up pies are possible within one move. Let's look at the sampled examples. So in this sampled examples, I have 1, 0, 0, 1, 1, 0. Initially, there are 4 pies facing up. Let's try the different moves to generate all the possible facing up pies. So I realize if I do nothing, there will be 4 pies facing up. If I flip the first pie, I end up with 3 pies facing up. If I flip the middle 2 pies, I end up with 6 pies facing up. If I flip all the 1 into 0, I end up with 1 pie facing up. And I can flip the middle 2 pie, then I end up with 5 pies facing up. Now I have 1, 3, 5, 6, 4 facing up pies. I might just ask myself, is 2 pies facing up possible? Yeah, so I find a way to achieve it. That is by flipping up all the pies from index 0 to 5. Then I end up with 2 pies facing up. So in total, I actually have 6. If you look at the output is 6. I have 6 different number of pies can end up facing up by just pick one continuous array and flip the pie. I have 1 pie facing up, 2 pie facing up, 3 pie facing up, 4 pie facing up, 5 pie facing up, 6 pie facing up. So I have 6 different number of ways or 6 different number of pies that can end up facing up. So what are the key observations we make here? We realize different moves can give the same result. Flip 6 and 6, just indexes, can end up giving me 5 pies. Or flip 1, 2, 3 can also give me 5 pies. So the question is not asking how many ways you can flip the pie. It's how many different distinct results can you get after flipping the pie. We can do by pure simulation, that is by picking all the possible starting point of the subarray, or the possible ending point for the subarray. That's going to be n squared. And for the input size of 10 to the power of 5, n squared solution is definitely not sufficient to pass the time limit. So how to optimize it? One key observations we see is when we flip a subarray, what changes to the original number of pi facing up? So each 0 in the range becomes 1. Now we have increasing the pi that's facing up. But for every 1 inside the subarray, it becomes 0, so it decreases the count for the pi facing out. Then the net changes after I flip this subarray is going to be the number 0 in this subarray minus the number 1 in that range. And we care about the net changes because the net changes create distinct possible pies end up facing up. So let's call the changes as deltas. Since we only care about delta, then let's transform the array into the delta. And we see every 0 is increasing 1 for our delta. Every 1 is decreasing 1 for the delta. So let's transform the original array into all +1 and -1, where 0 becomes +1, 1 becomes -1. And then we realize the delta of a subarray is just going to be the subarray sum of this transform array. Because let's say I decide to flip index 1, 2, that is this 0, 0. After the flip, I have gained 2 additional new pi facing up. And that's exactly equivalent to the subarray sum for the transform array, +1, +1, +2. So we realize we can calculate all the possible delta by calculating the subarray sums of this transform B. this is still not an improvement for the runtime because to calculate all the possible subarray sums, I still need an n-squared solution. It finally leads up to the critical realization that we don't need all the distinct subarray sums. All we need is the minimum delta, the maximum delta. So the minimum possible subarray sum and the maximum possible subarray sums. Why is that the case? Because here's my claim. All integers between the minimum subarray sums and maximum subarray sums are actually achievable. Why my claim is true? Because you start with 0. You start with nothing changed to the original pi facing up. And each flip is either a +1 or -1 to the subarray sum. And then from 0, you reach the minimum subarray sum. Also from 0, you can reach the maximum subarray sum. Since 0 is achievable, minimum is achievable, maximum is achievable, you can only do +1 -1 to navigate from the minimum possible number of possible sum to the maximum subarray sum. Then every integer in between is possible. Because if you go back to the transform array, let's say you have like a previous subarray sum of +1. Then from this +1, all you can walk is either +1 or -1. You can only do integer movement from the previous subarray sum. If you can go from 0 to minimum subarray sum, you can go from 0 to the maximum subarray sum, then surely every integer in between is achievable. Since every delta in between the minimum delta and maximum delta are achievable, then the final answer, the final net changes is just going to be max delta minus minimum delta +1. For example, if the minimum subarray sum is -3 and the maximum subarray sum is 2, then the answer is just going to be 2 minus -3 +1 equal to 6. So that's saying I can at maximum decrease 3 moon pi from the original pi facing up, and I can increase 2 to the current facing up pi. And all the combination in between I can achieve as well. Then I can create 3 pi's decrease, 2 pi's increase. The +1 comes from 0, no pi gain. That is, you flip nothing. So the answer has become, the algorithm has become, you first transform the original array into the +1 -1 array, where 0 is matched into +1, 1 is matched up into -1, because you care about net changes and you want to find all the possible net changes out there. Then we quickly realize the subarray sums are the net changes. And we only care for the maximum subarray sum and minimum subarray sum. And there is a famous algorithm called Pedan's algorithm that actually helps us to do so. Now, what's actually about this algorithm is quite intuitive. So after we have transformed the algorithm into +1 and -1, let's say we are aiming to find the maximum subarray sum. So we keep on expanding, we like about the +1. For every additional +1 I get, this current subarray sum might just be the new potential maximum subarray sum. So I just compare with the maximum subarray sum and update it along the go. But when my current subarray sum become negative, I should remind myself, let's start a new subarray. Why? Because you like about the +1 to create the maximum subarray. If your previous subarray sum is negative, all your future +1 is just going to be compensating for the previous negative value you have created, you have accumulated in the previous subarray sum. I might just as well start up with a new subarray, where the +1 is just going to be building up from a new subarray sum of 0. that's how I'm going to find the maximum subarray sum. Notice finding the maximum subarray sum in this way is going to only take us in a number of times, because you just need to go through every element in the transform array. The minus or the minimum subarray sum is just a little bit changes to the maximum subarray sum. So in this algorithm, we care about the -1. We want as much -1 as possible. We can tolerate some +1 in between until the +1 have made my subarray sum actually positive. When the +1 has accumulated too much for my current subarray, such that it's overcount the -1, that has made my current sum a positive value. In this case, I might just start up a new subarray for my new potential minimum subarray. Why? Because the new -1 that's coming up is just going to be canceling out the previous positive sum accumulated from my current subarray. I might just as well start a new subarray so my -1 can contribute based on a new subarray that has been a current sum of 0. So it's quite intuitive to implement it. The performance for this algorithm thus is reduced to over n compared to over n squared, because you only need to go through the transformed array one time to find the minimum subarray sum and maximum subarray sum, and then the answer is just going to be the maximum subarray sum minus the minimum subarray sum plus 1.